All right, now let's look at the next example. Let f of t equals t. Find Laplace transform f of t. And use it to find Laplace transform, let's say e to power minus 2t times t. The previous example told us how to find Laplace transform e to power minus at times f of t once we have the access to Laplace transform f of t. So once we find Laplace transform f of t, which we can do it using the definition of Laplace transforms, then we can use the previous example to find Laplace transform e to power minus 2t times t. So Laplace transform t, how can we calculate it? So Laplace transform t, Laplace transform f of t, we know that can be written as integral 0 to infinity e to power minus st f of t dt. So that means this is equal to f of t is t here. So integral 0 to infinity e to power minus st times t dt. So we need antiderivative of e to power minus st times t dt, which can be found using integration by parts. So to find integral e to power minus st times t dt, we can use integration by parts. How can we do that? So remember, integration by parts could be written as, let's say, integral u dv equals uv minus integral v du. So here we have integral t e to power minus st dt. I can write this one as integral t d e to power minus st divided by minus s. Because derivative dy is same as y prime dx. So d e to power minus st, d e to power minus st will be derivative of this function, which is minus s e to power minus st dt. So if I divide by minus s, I'll get e to power minus st dt. So I can replace this part. So t, I wrote it as t. I can write this part, e to power minus st dt. I can write it as d e to power minus st divided by minus s. So this is now in the form u dv. Well, this is a constant. I can take the constant out of the integral, but what will be left inside is integral u dv. Now, how can I write integral u dv? I can write it as uv minus integral v du. So this one I can write it as uv. So t, if we take the 1 over minus s out of the integral, then I can say uv, so t e to power minus st minus integral v du, integral v, which is e to power minus st du dt. This is my u, this is my v. So integral uv minus integral v du. Du will be dt. Now what will be integral e to power minus st? Antiderivative of e to power minus st is e to power minus st divided by minus s. So I can write it as, again, minus 1 over s is outside, t e to power minus st minus antiderivative of e to power minus st, which is e to power minus st divided by minus s. And then I can write this as minus 1 over s times t e to power minus st plus 1 over s e to power minus st. And I can write it as minus t e to power minus st divided by s minus 1 over s squared e to power minus st. So this is the antiderivative that we were looking for. Now we need to calculate this antiderivative between our limits, which are 0 and infinity. So we can say that the integral that we had, which was integral 0 to infinity, t e to power minus st dt is equal to limit as t goes to infinity of this antiderivative that we calculated here. This antiderivative e to power minus st is a common factor. I can take e to power minus st out, and then times minus t over s minus 1 over s squared. So I have to calculate the antiderivative at infinity minus calculate the antiderivative at 0. When we say at 0, we mean t equals 0. So if I replace t with 0 here, this term vanishes because 0 times anything is 0. And then I'll be left with e to power 0 is 1. I'll be left with plus 1 over s squared. So this term, this antiderivative at infinity, which is this term, minus this antiderivative at t equals 0. This antiderivative at t equals 0 will be minus 1 over s squared. So minus 1 over s squared will become plus 1 over s squared. Now, how do we calculate this limit? Or how do we know whether the final answer will be convergent or divergent, depending on the value of s? So if s equals 0, so let's again see different possibilities. If s equals 0, this integral will be divergent. Why? Well, some people say if s equals 0, we cannot have 0 denominator, but we don't need that. If s equals 0, just look at the original expression. This is the original expression for the Laplace transform. If s equals 0, this will be 1. And integral 0 to infinity t dt is divergent according to what we learned in Math 114. So then in this case, I can just simply say because integral 0 to infinity t dt is divergent. Now, what about if s is less than 0? If s less than 0 minus means s is negative, minus s becomes positive. So this becomes e to power infinity, which is infinity. And this will become how much? This become minus infinity over a negative number, becomes positive infinity. Positive infinity minus, this will be a constant. Positive infinity minus a constant will be infinity. This will be infinity times infinity will be infinity. So let me write it down how I calculated. So this will be divergent again if s less than 0, because e to power infinity times infinity minus 1 over s squared will become e to power infinity times infinity, which will be infinity. So let me explain one more time how I calculated this limit if s is less than 0. If s is less than 0, e to power minus s will be positive. E to power infinity, this term will be e to power infinity, which is what I wrote here. What about this term inside bracket? If s is less than 0, minus s will be positive. So this minus 1 over s will be positive times t goes to infinity. Positive number times infinity will be infinity. So that's why I wrote infinity here. Minus 1 over s squared, I wrote it down again because it does not depend on t. Now, s is a constant. Remember, the limit is over t. So infinity minus a constant is still infinity. Infinity plus a constant or infinity minus a constant is infinity. This is what you learn in math 113. So this will be still infinity. So this will be infinity times e to power infinity times infinity. But e to power infinity itself is infinity. Infinity times infinity is infinity. So this time will be infinity plus a constant will be still infinity. So that's why we said in this case, if s is less than 0, your integral will be divergent. And finally, if s is bigger than 0, what will I have? The answer will be, in that case, 1 over s squared. If s is bigger than 0. Why? Because if s is bigger than 0, this term will be e to power minus infinity. E to power minus infinity times, and t goes to infinity. So this will be minus infinity over a constant. So minus infinity over a constant minus a constant will be minus infinity. So this will be minus infinity times e to power minus infinity. E to power minus infinity is 0. So 0 times infinity. 0 times infinity is indeterminate. And we need to simplify it. You sign math 113. If you have an indeterminate form, you need to simplify either using L'Hopital rule or some other way. So this is, let me say, this will be e to power minus, let me say this will be 0 times infinity, which is indeterminate and needs to be simplified. So let me simplify here below. So C below. So let's see what happens if limit as t goes to infinity. So let me say justifying that limit as t goes to infinity, e to power minus st times this expression, which is minus t over s minus 1 over s squared. This will be 0. My claim is this is 0, this limit. I will verify it using L'Hopital's rule. Because I have to use L'Hopital rule because we just saw it's 0 times infinity and it's indeterminate. We have to use L'Hopital rule or another way to simplify, but in any case, it has to be simplified. And once we simplify and we verify that this limit is 0, then 0 plus 1 over s squared will be simply 1 over s squared. And this will be valid if s is bigger than 0. So how can I justify that this limit is 0? Well, left-hand side here will be limit as t goes to infinity minus t over s minus 1 over s squared divided by e to power st. So I'm using a very simple fact that e to power minus st can be written as 1 over e to power st. And here I have now infinity over infinity, so I can use L'Hopital's rule. Will tell me that this is limit derivative of top. L'Hopital's rule says derivative limit of a fraction, if it's of the form infinity over infinity or 0 over 0, can be written as limit of derivative of top over derivative of bottom. What is derivative of top? Respect to t. Everything is respect to t. Limit is over t. So derivative has to be also respect to t. What is derivative of top respect to t? It's minus 1 over s divided by derivative of bottom respect to t is s e to power st as t goes to infinity. And then this will be minus 1 over s divided by s times infinity. Because remember, s is positive. I'm assuming s is positive. So as t goes to infinity, this goes to e to power infinity. S is positive, positive times infinity will be infinity, e to power infinity will be infinity. So I have, and remember s is a constant. So constant over infinity. Constant over infinity, this will be 0. S here is constant. Everything was over t, limit was over t. S is a constant, constant over infinity is 0. So we showed that this limit is 0. If s is positive, 0 plus 1 over s squared will be 1 over s squared. So overall, what did we show? So we showed that Laplace transform t is equal to 1 over s squared if s is positive and is undefined if s is less than equal to 0. So that means the domain of f of s equals Laplace transform t is 0 to infinity. Now we can use this part to find Laplace transform e to power minus 2t times t, which was asked in the question. Laplace transform e to power minus 2t times t. So we can say thus Laplace transform e to power minus 2t times t is equal to capital F of s plus 2, which is going to be 1 over s plus 2 the whole squared. Because we know that Laplace transform of e to power minus at f of t is equal to capital F of s plus a. So as an exercise, now you can try to find Laplace transform t squared. Laplace transform t squared, you can show that is equal to 2 over s cubed for s bigger than 0. And for s less than equal to 0, again, it's going to be undefined. Which can be again found using integration by parts, similar to what we did for Laplace transform t. And similarly, if you continue this, the general rule, Laplace transform t to power n, it can be shown that is equal to n factorial over s to power n plus 1. So if you think about it, Laplace transform 1, if n was 0, so this n here can be considered to be bigger than or equal to 0. So if n equals 0, then we will have Laplace transform 1, which we saw it was 1 over s. And this formula gives us 0 factorial over s. 0 factorial, we know it's 1. So 1 over s, which is what we saw before. And if n is equal to 1, then we'll have Laplace transform t equals 1 over s squared, which is again what we saw before. Laplace transform t squared will be 2 over s cubed, which is what is asked in the previous exercise. Similarly, Laplace transform t cubed, for example, if we use this formula, Laplace transform t cubed will be 3 factorial over s to power 4. And 3 factorial means 6. So it will be 6 over s to power 4, and so on. We can similarly find Laplace transform t to power 5, t to power 4, 5, 6, and so on. So this is a general rule for Laplace transform t to power n. And again, this is true. This is valid for s bigger than 0. And for s less than or equal to 0, again, this Laplace transform will be undefined. Now let's look at the next example, Laplace transform sine t. Let's see how we can find Laplace transform sine t. So what is the formula for Laplace transform sine t? Again, we know Laplace transform sine t is equal to integral 0 to infinity e to power minus st times sine t dt. And again, we need the antiderivative for e to power minus st sine t, which can be found using integration by parts. So now, to find the antiderivative or indefinite integral, we know antiderivative is same as indefinite integral. So to find indefinite integral e to power minus st sine t dt, we can use the integration by parts. Now again, integral e to power minus sine st sine t dt. I can write it as integral sine t d e to power minus st divided by minus s, similar to what we did for the previous example. Because we know d e to power minus st will be derivative of that function e to power minus st, which is minus s e to power minus st times dt. And minus s will cancel with minus s in denominator. I'll be left with e to power minus st dt. Now I have integral u dv. I can write it as uv minus integral v du. So I can write this one as, again, minus 1 over s can be taken out of the integral. And then sine t e to power minus st. And then minus integral e to power minus st d sine t. My u here is sine t, so uv minus integral v du. V du, so it's going to be v e to power minus st d sine t. Now, what is d sine t? D sine t, we know it's cos t dt. D sine t will be derivative of sine t times dt. So it will be cos t dt. So then this will be minus 1 over s sine t e to power minus st minus integral e to power minus st times cos t dt. Now, what about this integral e to power minus st cos t dt? How can I simplify it? So I can simplify it as, so similarly, you can check that integral e to power minus st cos t dt can be written as minus 1 over s e to power minus st cos t minus 1 over s integral e to power minus st sine t dt. So we can do a similar calculation that we did for integral minus st sine t dt. You can do it for integral minus st cos t dt. And you can show that it can be written this form. Now, if we substitute this back, now substitute back And then what do we get? So see here, I needed integral e to the power minus st cos t dt. I couldn't find this integral, but I could write it in this form in terms of integral e to the power minus st sine t dt. So if I substitute back here, what do we get? So we get integral e to the power minus st sine t dt equals minus 1 over s is outside, so minus 1 over s times inside we will have sine t e to the power minus st sine t e to the power minus st minus this integral, which was minus 1 over s e to the power minus st cos t minus 1 over s, this integral. So it's going to be minus this expression, so it becomes plus 1 over s e to the power minus st cos t, and then plus 1 over s integral e to the power minus st sine t dt. So we haven't been able to calculate this integral explicitly, but we could find it in terms of itself. So if you have a variable, if you have an unknown variable that you can find it in terms of itself, let's say if you can find out that x is equal to, let's say, 2x plus 1, finding x in terms of x itself. So that gives you one equation with one unknown, and you can isolate for that unknown and try to find it. So here, if I set this integral, let's say I can call it I, or you can call it x, whatever you like. Let's say I equals integral e to power minus st sine t dt. Then what do we have? Then we will have I equals minus 1 over s times sine t e to power minus st. So minus 1 over s times, I can take e to power minus st out. So, or I can write it as e to power minus st sine t. And then minus 1 over s times 1 over s becomes minus 1 over s squared. So minus 1 over s squared e to power minus st cos t. And then minus 1 over s squared times I. Minus 1 over s squared times I. See, minus 1 over s times 1 over s becomes minus 1 over s squared. And this integral is what I called it I, and that's what I want to find. So then what do we have? Then we will have I equals I can isolate for I because I want to find I. So let's take all the terms that contain I into one side. So this term contains I and this term contains I. Let me take this term to the left-hand side. Then becomes I plus 1 over s squared times I equals e to power. The right-hand side becomes minus 1 over s e to power minus st sine t minus 1 over s squared e to power minus st cos t. Or if I factor I out, then 1 plus, what will be left? 1 plus 1 over s squared. 1 plus 1 over s squared, if I take common denominator, can be written as s squared plus 1 over s squared equals minus 1 over s e to power minus st sine t minus 1 over s squared e to power minus st cos t. So then this gives me the value of I. I will be equal to s squared over s squared plus 1 times, now these two terms, I can take minus 1 over s times e to power minus st out as a common factor. So minus 1 over s times e to power minus st. And what will be left? Sine t will be left from the first one. And then plus cos t over s will be left from the second one. And I can simplify it further, because minus 1 over s times s squared will be s minus s. So minus s over s squared plus 1 times e to power minus st times sine t plus cos t over s. Now, this was the integral that we wanted to calculate. This was the antiderivative. Now we need to calculate this integral between 0 and infinity. Remember that originally we had integral 0 to infinity. 0 to infinity of this expression. We found the antiderivative. Now we need to find, calculate or evaluate the antiderivative between 0 and infinity. Then what do we get? Integral 0 to infinity e to power minus st sine t dt will be equal to this expression evaluated at infinity minus evaluated at 0. So it's going to be minus s over s squared plus 1 times limit e to power minus st times sine t plus cos t over s as t goes to infinity. And then minus evaluate at 0. If I evaluate this guy at 0, e to power 0 is 1, sine 0 is 0, cos 0 is 1. So it will be 1 over s times this becomes minus 1 over s squared plus 1. But it's minus that, because I need to evaluate, if I want to find the integral 0 to infinity, I need to evaluate the antiderivative at infinity minus an antiderivative at 0. Antiderivative at 0 is minus 1 over s squared plus 1, but it's minus that, so it becomes plus 1 over s squared plus 1. So it becomes this guy plus 1 over s squared plus 1. And then, now what will be the answer? So again, the answer depends on the value of s, like the previous times. Now, what will be the answer? Will this expression be, will it be convergent or divergent? My claim is that this expression will be divergent. If s is less than or equal to 0, and it will be convergent if s is bigger than 0. So it's divergent if s equals 0. If s equals 0, again, we can use the original definition of Laplace transform here. If s equals 0, I will have integral 0 to infinity sine t dt, which you learned that is divergent in Math 114. Integral 0 to infinity sine t dt is divergent. That's what you learn in Math 114. So again, we don't need any of these calculation in the case that s equals 0. So I can simply say, because integral 0 to infinity sine t dt is divergent, which is what you saw in Math 114. Now, if s is less than 0, again, it will be divergent. If we say C below, I'm going to do the calculation after this. And if s is bigger than 0, it will be convergent, and it will be convergent to 1 over s squared plus 1. So 1 over equals 1 over s squared plus 1 if s bigger than 0. So again, C below. So I still need to justify these two claims that if s less than 0, the expression will be divergent. If s bigger than 0, it's convergent, and convergent to 1 over s squared plus 1, which will be this term. Basically, I need to show that if s bigger than 0, this term here will be 0, and then 0 plus this will be 1 over s squared plus 1. So I need to justify two things. So justifying divergence in the case of s less than 0. If s less than 0, what can we say? If s less than 0, that means s is a negative number, so minus s becomes a positive number, and this becomes e to power infinity. But then this is not a constant. This will be sine infinity, cos infinity. So how can I show that overall this limit will not exist, or it will not be convergent? So to show that limit e to power minus st times sine t plus cos t over s as t goes to infinity is divergent. Let's use proof by contradiction. Suppose that on the contrary, this limit is convergent to some value, let's say L. So in math 113, you saw that if you have a limit, if limit of a function exists and is equal to some L, then limit of any sequence, let's say, then we can say limit of f of Tn will be also convergent to L for any sequence Tn that goes to infinity. So if limit of the function as t goes to infinity is equal to L, limit of f of Tn has to be also equal to L for any sequence Tn that goes to infinity. Then, so we can say then limit e to power minus sine e to power minus stn times sine tn plus cos tn divided by s as n goes to infinity will be also L, will be also convergent to L, will be convergent to L for any sequence, Tn with Tn goes to infinity. So if this limit, this is what you learn in math 113, limit f of t, let's say is t goes to infinity is L, then limit f of Tn as n goes to infinity must be also L for any Tn that goes to infinity. So that means if I can find a particular sequence Tn that goes to infinity, but this limit is not convergent to any value L, then I will have my contradiction, and then that means this original limit must be divergent, because if it was convergent, then we would have a contradiction. Now, how can I find a sequence Tn that goes to infinity and this limit is divergent? Is this sequence is not convergent to any number L? Well, for example, let's say if I choose my Tn to be, let's say 2n pi, then sine 2n pi is 0, cos 2n pi will be 1. And so this expression, it will be always 0 plus 1 over s, which is 1 over s. And 2n pi times minus s. Remember, s right now we're assuming it's negative, so minus s is positive. So e to power positive number times 2n pi becomes, as n goes to infinity, becomes a positive number times infinity, e to power infinity times, and this expression becomes 1 over s, which is a constant, and then e to power infinity times a constant will be still infinity. So it won't be convergent to L for any value L because it will be divergent in that case. So now let me say that we can consider let's say Tn equals 2n pi then as n goes to infinity, Tn goes to infinity. So Tn is an example of a sequence that goes to infinity as n goes to infinity. And what can I say about this expression? What will be e to power minus stn sine tn plus cos tn over s? And limit as n goes to infinity of e to power minus stn times sine tn plus cos tn divided by s will be equal to limit n goes to infinity, e to power minus s times 2n pi sine 2n pi plus cos 2n pi divided by s. Remember, n here is a positive integer. So sine 2n pi will be 0, cos 2n pi will be 1. So then this will be limit e to power minus s times 2n pi times 1 over s. Because this guy is 0, this will be 1. Overall will be 1 over s. Now minus s is positive because s is negative. So then I'll have e to power positive number, n goes to infinity, positive number times infinity will be infinity. So I will have e to power infinity times 1 over s, which will be infinity. E to power infinity times 1 over s, that will be infinity. And this is contradiction with this sequence converging to L. Remember, this sequence was supposed to be convergent to L, but the limit of it is infinity, so it's divergent. So it's a contradiction. So this contradiction shows that the original limit that we were considering here must be divergent, because if it was not divergent, then we would have contradiction. So this shows that the integral above, which was integral 0 to infinity e to power minus st sine t dt, is divergent in this case. Remember that this integral, which was same as Laplace transform, we saw that we showed that is equal to this expression plus 1 over s squared plus 1. But we just showed that this expression in the case of s less than 0 is divergent. So this whole expression, once you multiply with a constant, you add with another constant, still it will be divergent. So in this case, this will be divergent. In this case, I mean, if s is less than 0. If s is less than 0, this integral will be divergent. Now, what about if s is bigger than 0? So let's justify that the integral is convergent in that case. So justifying integral 0 to infinity e to power minus st sine t dt is convergent. And we said it's convergent to, if you remember, we said it's convergent to 1 over s squared plus 1 if s is bigger than 0. So convergent to 1 over s squared plus 1 if s bigger than 0. How can I verify or justify this? Well, we have to look at the limit that we had there. So if I show that this limit is convergent to 0, then times this will be still 0 plus this constant will be 1 over s squared plus 1. So we just need to show that limit e to power minus st times sine t plus cos t over s as t goes to infinity is equal to 0. And how can I verify this? So let's start with, I want to use the squeezing theorem. Now, what can I say about sine t and cos t? I know that sine t and cos t, both of them are between -1 and 1. So we know that sine t is between -1 and 1, and cos t over s will be between -1 over s and 1 over s. Remember, s is a positive number. So if cos t between -1 and 1, you can divide everything by s, and you get cos t over s between -1 over s and 1 over s. And then this means that sine t plus cos t over s will be between -1 over s and 1 plus 1 over s. And if I multiply everything by e to power minus st, then I will have e to power minus st times -1 over s less than equal to e to power minus st times sine t plus cos t over s, and less than equal to e to power minus st times the expression on the right-hand side, which is 1 plus 1 over s. And then now, if I look at the limit of this expression and this expression as t goes to infinity, remember, the limit is over t, s is considered as a constant. So this is a constant times e to power minus infinity, which is 0. This is also a constant times e to power minus infinity, which is 0. So I will have my function squeezed between two functions where both limit of both of these functions is 0. So that means limit of the middle function also must exist and must be equal to 0 according to the squeezing theorem. So now limit e to power minus st times -1 over s as t goes to infinity is equal to limit e to power minus st times 1 plus 1 over s as t goes to infinity. And both of them are 0 because e to power minus infinity is 0. This is because s is bigger than 0 and e to power minus infinity is 0. So by squeezing theorem, we can say that limit e to power minus st times sine t plus cos t over s as t goes to infinity exists and is equal to 0. Because it's squeezed between two functions, where the limit of both those two functions is 0. So limit of middle function must exist and must be equal to 0. So what did we show overall? So we showed that Laplace transform sine t is equal to 1 over s squared plus 1 if s is bigger than 0 and is undefined if s is less than or equal to 0. So again, we can say that the domain of this Laplace transform, again, it's 0 to infinity, open interval 0 to infinity. So the domain of capital F of S equals Laplace transform sine t is open interval 0 to infinity. Now, similarly, we can find Laplace transform, let's say, sine omega t. So right now we calculated Laplace transform sine t, which was 1 over s squared plus 1. So similarly, as an exercise, we can try to show that Laplace transform sine omega t, where omega is a constant, is equal to omega over s squared plus omega squared, if again s bigger than 0. Here omega is a constant. And another exercise, we can show that Laplace transform cos omega t, Laplace transform cos omega t will be equal to s over s squared plus omega squared. Again, if s is bigger than 0, again, omega here is a constant. So again, in particular, if omega is 1, then we can say that Laplace transform cos t is s over s squared plus 1. So Laplace transform sine t is 1 over s squared plus 1. Laplace transform cos t is s over s squared plus 1. Now another example, let's say Laplace transform sine hyperbolic t is equal to 1 over s squared minus 1. How can we show this? So first of all, we need to remind ourselves about the definition of sine hyperbolic. What was the definition of sine hyperbolic t? Sine hyperbolic t, we know that it can be written as e to power t minus e to power minus t divided by 2. And cos hyperbolic t, we know that can be written as e to power t plus e to power minus t divided by 2. So if you want to find Laplace transform sine hyperbolic t, this will be Laplace transform e to power t minus e to power minus t divided by 2. And next time we will see that Laplace transform is a linear transformation. I already mentioned at the beginning of today's lecture that it's linear, but next time we'll prove that it's linear. And once we show it's linear, it means that Laplace transform of addition of two functions is addition of Laplace transforms. And also it means that if there is a constant involved, you can take the constant out. So next time we'll see that Laplace transform will show that Laplace transform is linear. So then we can write this one as 1/2 times Laplace transform e to power t minus Laplace transform e to power minus t. We write it the next line. 1/2 times Laplace transform e to power t minus Laplace transform e to power minus t. And we know that Laplace transform e to power at is 1 over s minus a. We already saw this. So I can write this one as 1/2 times 1 over s minus 1 minus 1 over s plus 1. And if I simplify this, this is true for s bigger than this is valid if s is bigger than a. So that means that this will be valid for s bigger than 1. This will be valid for s bigger than minus 1. So both of them must be valid so that I can say that this formula is valid. So if s is bigger than 1 and s bigger than minus 1, overall means s bigger than 1. So this formula is valid if, I can write it here. If s is bigger than 1 and s bigger than minus 1, meaning that s bigger than 1. The intersection of s bigger than 1 and s bigger than minus 1 is s bigger than 1. And in that case, I will have 1/2 times 1/2 times s plus 1. Now the common denominator is s squared minus 1. And numerator will be s plus 1 minus s minus 1. And this will be 1/2 times 2 over s squared minus 1, which is 1 over s squared minus 1. So this will be valid if s bigger than 1. So we showed that Laplace transform sine hyperbolic t is 1 over s squared minus 1 if s bigger than 1. And for s less than or equal to 1, it will be undefined. So Laplace transform sine hyperbolic t is equal to 1 over s squared minus 1 if s is bigger than 1. Similarly, as an exercise, you can try to calculate Laplace transform cos hyperbolic t or sine hyperbolic or cos hyperbolic omega t. So again, let me leave them as exercise to show that Laplace transform sine hyperbolic omega t is equal to omega over. This will be equal to omega over s squared minus omega squared if s is bigger than omega. And similarly, you can show that Laplace transform cos hyperbolic omega t is equal to s over s squared minus omega squared if s is bigger than omega. And in particular, if you look at Laplace transform cos hyperbolic t, it will be s over s squared minus 1 for s bigger than 1. So here again, omega is a positive constant. You can assume that this is a positive constant. And finally, we also want to find Laplace transform of one more function, which is called a step function. So another example, Laplace transform of the step function, also called a Heaviside function. Heaviside function. So let's look at the definition of this function, step function or Heaviside function first, and then we can find the Laplace. We can find its Laplace transform. So note that the step function denoted by u of t is defined as follows. U of t, we define it as 0 if t is less than 0. U of t equals 0 if t less than 0. And we define it as 1 if t is bigger than or equal to 0. So this is how we define the step function. 0 for t less than 0, 1 if t is bigger than equal to 1, if 1 if t is bigger than equal to 0. So what can we say about u of, let's say, t minus a? So this is a step function, the standard step function, which has the border point of 0. Whatever if the border point is, let's say, some a with some constant a. So thus u of t minus a for some constant a will be defined as u of t minus a will be equal to 0 if t minus a is less than 0, which means t is less than a, and it will be 1 if t minus a is bigger than equal to 0, which means t bigger than equal to a. So u of t minus a, in other words, it's 0 if t is less than a, and it's 1 if t is bigger than or equal to a. So this function has applications in Laplace transform and in physics as well. Now let's see whether we can find the Laplace transform of ut minus a if a is bigger than equal to 0. So now suppose that a is bigger than equal to 0, and find Laplace transform ut minus a. So Laplace transform ut minus a will be how much? So Laplace transform ut minus a will be equal to integral 0 to infinity e to power minus st u of t minus a dt. And this one we can write it as integral 0 to infinity e to power minus 0 to, let me break down the integral. It's 0 to infinity. I can write it the integral as 0 to a and then a to infinity. So integral 0 to a e to power minus st, but for t less than a, the function is 0, ut minus a is 0. So e to power minus st times 0 dt. And then from a to infinity, it will be 1 dt. So this will be 0 because 0 times anything is 0. So I'll be left with integral a to infinity e to power minus st dt. And I can write this one as limit, let's say h goes to infinity. Or let me find the antiderivative of e to power minus st, which is e to power minus st over minus s from 0 to infinity. So I can write this one as limit e to power minus st t goes to infinity over minus s plus, so this one is a to infinity, plus e to power minus sa over s. So I need to calculate this one at infinity, which means I need to calculate this limit, minus evaluation of this at a. This one at a is e to power minus sa over minus s, but it's minus that, so it becomes plus e to power minus sa over s. Now again, this one, if s is positive, like the previous examples, if s is positive, we can say that the first term is 0. So limit e to power minus st as t goes to infinity is 0 if s is positive. So then I'll have e to power minus SA over S will be my final answer if S is positive. So we show that Laplace transform U of t minus A is equal to e to power minus SA over S if S is positive, and again is undefined if S is less than or equal to 0. And here, as we said, U of t minus A is the step function, which can be written as 0 if t is less than A, and it will be equal to 1 if t is bigger than or equal to A. So if you define the step function this way, then Laplace transform of this function will be e to power minus SA over S. We'll see the application of this formula later, and we'll see later how we can use the step function to solve differential equations. So overall, if I want to summarize what we have done today, we have derived the table. We talked a little bit about Laplace transform and how why it's important. You know, the input and output are functions, but what's the point of applying such a transform to go from basically T's, universe of T's to universe of S's, where there will be no derivatives appear there. I'll show this next time for you that once you apply Laplace transform, the derivatives will be disappeared. But I just wanted to tell you about the general idea in the beginning of the lecture, that why this Laplace transform is important or how it can be used to solve differential equations. We will see the details later. But for now, for today, most of our time was spent for finding Laplace transform of specific functions. For example, Laplace transform of polynomials, or Laplace transform of trigonometric functions, or Laplace transform of step function in this case. So in general, in summary, if I want to summarize, so we derived the following table. For Laplace transforms. So we saw that if the function, let's say if you have our table had two columns, f of t and Laplace transform of f of t, which is also denoted with capital F of s. So we saw that if the f of t function is 1, then Laplace transform is 1 over s. If it's t, it will be 1 over s squared. If it's t squared, it will be 2 over s cubed. And if it's, let's say, t to power n in general, it can be written as Laplace transform can be written as n factorial over s to power n plus 1. And for sine omega t, we saw that sine omega t, Laplace transform was omega over s squared plus omega squared. For cos omega t, it was s over s squared plus omega squared. For sine hyperbolic omega t, it was omega over s squared minus omega squared. For cos hyperbolic omega t was s over s squared minus omega squared. For e to power at, it was 1 over s minus a, if you remember. For e to power at times f of t was, or let's say e to power minus at times f of t was capital F of s plus a. Or if you want this to be consistent with this, I can say for e to power at, f of t, I can write it as capital F of s minus a with capital F of S being Laplace transform of f of t. So this is a special case of this. If f of t is 1, then according to this formula, Laplace transform of e to power at will be f of s minus a, where f of s is Laplace transform of 1, which is 1 over s. If f of s is 1 over s, f of s minus a will be 1 over s minus a, which is what we saw here. So we derive these formulas as well. And finally, for u of t minus a, the step function, u of t minus a, we saw that Laplace transform can be written as e to power minus sa divided by s. So these are about, the Laplace transform of specific functions. Next time we will see for which functions we can guarantee existence of Laplace transform, and also whether Laplace transform is one-to-one, and if it's one-to-one, then can we apply inverse Laplace transform to get the original function back once we find the Laplace transform of a given function. Okay, guys, so that's all for today. Thank you and see you next time.